Hey everyone, and welcome to This Explainer. Today, we're taking a really fascinating journey straight into the architecture of modern artificial intelligence. We're going to take those dense academic concepts, the heavy mathematical models, and translate them into a highly visual, accessible journey. My whole goal here is to completely demystify artificial neural networks for you. We'll be using our primary source material to show you exactly, and I mean exactly, how these incredible systems are built right from the ground up.
Okay, let's dive into our roadmap. We'll be going sequentially through 5 stops today: brain versus the machine, inside the artificial neuron, network topologies explained, how neural networks learn, and finally, real-world applications and limits.
So, starting with section 1, brain versus the machine, we really need to look at the biological roots of modern computing first.
Just look at the sheer contrast here between a biological machine and a synthetic one. These stats from our source are just wild. The human brain packs in roughly 86 billion neurons, firing entirely asynchronously. And get this, it consumes a mere 20% of your body's energy. That means your incredibly powerful adult brain operates on about 20 watts. To put that into perspective, that's barely enough juice to dimly light a standard light bulb. On the flip side, artificial neural networks operate synchronously, meaning everything ticks rigidly to a clock. And man, they are power-hungry. A single NVIDIA GeForce GPU used to run these networks devours 250 watts all by itself. So yeah, while our machines are definitely getting smarter, they are still vastly less efficient than the biological hardware inside our own heads.
To see where the inspiration for these artificial systems actually comes from, let's look at the real thing. Check out this biological neuron. See those sprawling tree-like branches? Those are the dendrites. And that's where the majority of input to the neuron actually happens. The information flows right into the cell body, the soma. And if the electrical voltage changes by a large enough amount, boom, the neuron generates an all-or-nothing electrochemical pulse. We call that an action potential. That signal shoots rapidly down that long tail you see, the axon, to communicate with other cells. It's just a beautifully complex organic system.
But right here is where the engineering magic happens. We completely flatten that messy biological wetware into a clean, mathematical artificial neuron model. In an artificial network, we just strip away all the biology and rely on 3 basic rules: multiplication, summation, and activation. Inputs arrive, they get individually multiplied by a specific weight, they're all summed up together along with a bias, and then, finally, that number gets pushed through an activation function to spit out an output. It's literally an elegant mathematical imitation of life.
Which brings us to section 2, inside the artificial neuron. Let's see how we actually translate that anatomy into mathematics.
So, the absolutely crucial point here is that this activation function acts as the extra force applied over an input to bound the final output. Think about it. If we just added numbers together, our network would literally just be drawing straight, linear lines. And as we know, real-world data isn't linear at all. Activation functions, like the sigmoid function, which basically squashes outputs between 0 and 1, give the neural network its nonlinear learning ability. It helps the network decide, purely mathematically, whether a neuron should fire or not. It's totally mimicking that biological action potential we just talked about.
Let's make this a bit more tangible, right? We can actually look all the way back to 1943 when Warren McCulloch and Walter Pitts published the very first paper describing what we'd now call a neural network. We can use their model, the McCulloch-Pitts linear threshold gate, as a relatable analogy. Let's use it to mathematically predict a simple binary decision. Will you watch a random football game on TV?
In this model, all inputs are Boolean, so simply a 0 or a 1. Let's walk through these. Input x1 is the Premier League on? Now, assuming you love the Premier League, this is an excitatory input. It pushes the neuron closer to firing. Input x2 is it a knockout game? Another excitatory input. But look at x3, am I not home? This right here is an inhibitory input. Obviously, if you aren't home, you physically cannot watch the TV. Therefore, this single inhibitory input immediately forces a 0 output. It completely kills the chance of firing the neuron, no matter how many excitatory inputs are turned on. It perfectly mirrors our own human decision-making constraints, but just using basic arithmetic.
Moving on to section 3, network topologies explained. This is where we connect the individual nodes into functional networks.
You can really notice the leap in complexity here. On the left, we've got a single-layer feed-forward network. Information simply flows in one direction, directly from the input layer straight to the output layer. But on the right side, we have a multi-layer feed-forward network. See that column of nodes sandwiched right in the middle? We call that a hidden layer. By adding hidden layers, we drastically increase the network's ability to recognize incredibly complex patterns in the data. But notice, in both of these feed-forward topologies, the signal only ever moves forward. It's basically a one-way street.
But what if the streets weren't one-way? Enter the fully recurrent feedback network. Unlike those one-way streets we just looked at, a recurrent network actually allows signals to loop continuously. The nodes can act as both input and output. This creates a highly nonlinear dynamic system that constantly changes and updates itself until it finally reaches a state of equilibrium. It's just a completely different way of processing information, and it's absolutely excellent for tasks where past context matters.
Okay, Section 4. How neural networks learned. Let's look at adjusting those weights and finding patterns.
According to our source material, a network actually adjusts its weights through one of three learning paradigms. First up, there's supervised learning. This is kind of like having a teacher. The network makes a guess, the teacher checks that actual output against the desired output, generates an error signal, and the network corrects itself. Second is unsupervised learning. Now, there is no teacher here. The network independently discovers patterns and forms clusters from similar input data all on its own. And finally, there's reinforcement learning. Here, the network doesn't have the exact right answers handed to it, but it receives evaluative feedback, essentially a reward or a penalty, from its environment over time to strengthen good behaviors.
So when that error signal is generated in supervised learning, how does the network actually fix itself? Well, it happens through a process called backpropagation. Now, you can break down this dense mathematical jargon simply as the reverse gear of the network. Once a prediction is made, the network actually works backward. It tracks derivatives to discover just how far off it was. Then, it uses a mathematical process called gradient descent to constantly tweak the weights of individual neurons until the overall error function shrinks down to a minimum. It literally learns from its mistakes.
Let's see how this builds upon one of the oldest concepts in the entire field, the Hebbian learning rule. This was developed by Donald Hebb way back in 1949. It's an unsupervised method which dictates a beautifully simple logic. Basically, you start with all the weights set at 0. If the network observes that two neighbor neurons are activating and deactivating at the exact same time, it mathematically assumes they're related and it bumps up the weight connecting them. Simply put, and you might have heard this before, neurons that fire together wire together.
And finally, Section 5, Real-World Applications and Limits. This is where theory meets reality.
These artificial neural networks are already incredibly successful out in the wild. In aviation, airlines use expert systems and neural networks to monitor atmospheric conditions so effectively that planes can basically fly on autopilot once a course is set. In the medical field, networks are identifying complex diseases from CAT and ultrasonic scans. And the real beauty there? The doctors didn't even have to program the algorithms. The networks learned by example. And in finance, oh man, it's highly lucrative. A company called HNC implemented a neural network credit scoring system that actually bumped business profitability by an impressive 27%. The real-world value is just undeniable.
But hey, I want to be perfectly clear about something. Artificial neural networks aren't magic. As our source notes, they actually have very strict limitations. First off, they require an immense computational burden. Just remember that 250-watt GPU we talked about earlier. They're also prone to overfitting, which means they can memorize their training data so well that they just fail completely when presented with new, unseen data. But most importantly, they are highly specialized. Unlike the incredibly adaptable human brain that can learn to play chess and then immediately go learn to cook a meal, an ANN designed for credit scoring is completely useless at anything else. They are definitely not general-purpose, daily-life problem solvers. And that brings us to the most fascinating limitation of all, and it's one I'm going to leave you to ponder today. Many neural networks suffer from what's known as the black box problem. Because they develop their own internal representations through thousands and thousands of weight adjustments, they literally cannot explain their reasoning to us. So my final question to you is this. Can we truly trust a system, whether it's diagnosing our diseases or flying our airplanes, that perfectly solves complex problems, but fundamentally cannot describe to us how it solved them? Thank you so much for joining me on this explainer. I really hope it sparked your curiosity, and I definitely encourage you to keep exploring the incredible world of neural networks.